Today we will discuss organometallic chemistry. Today we will start with the organomagnesium reagents. What are organometallic reagents? Organometallic reagents are basically carbon, metal, in organometallic reagents, there will be an ionic bond between carbon and metals. So that will be utilized for carbon-carbon bond formation reactions. Now, based on the polarity of carbon-metal bond, organometallic reagents are classified into three categories: more less polarity or more covalent. Generally, carbon, lead, carbon, mercury, whose electronegativities are almost similar to carbon. So they'll have less electronegativity differences. So that is why these carbon metal bonds are less polar, or we can say more covalent. Intermediate polar. That means electronegativity differences between carbon and metal will increase little bit further. Generally, copper, lithium, copper, magnesium, copper, zinc, carbon, lithium, carbon, magnesium, carbon, zinc, carbon, copper. All these carbon metal bonds will come under this category. Because of their polarity, these reagents are used for carbon-carbon bond formation reactions. And finally, we have more polar carbon metal reagents. These are carbon, potassium, carbon, sodium. So these can be used as bases. These can be used as both as bases as well as nucleophiles. These cannot be used because of their less polarity. Now we will look at the useful organometallic reagents and their percentage of ionic character. When we look at the lithium, whose electronegativity is 0.97, so its percentage of ionic character, that means carbon lithium bond percentage of ionic character, is 43%. When we look at the magnesium, whose electronegativity is 1.23, so its percentage of ionic character is 35%. You don't need to remember all these values. You just remember them by comparison, okay? Which is more ionic bond, which is less ionic bond. So you just look at these values in a comparative way. So carbon aluminum bond is 22% ionic in nature. Carbon zinc bond is 15% ionic in nature. Carbon copper bond is 12% ionic in nature. Similarly, carbon silicon bond is 12% in ionic in nature. Carbon tin bond is 11% ionic in nature. So when we compare these things, carbon lithium bond is more ionic in nature than magnesium, titanium, aluminum, zinc, copper, silicon, and then tin. You just compare them. Okay, we don't need to remember any of these values. Now we will start with Grignard reagents. Grignard reagents were discovered by Victor Mayer Grignard. He discovered them in 1900, and for his discovery, he got the Chemistry Nobel Prize in 1912. So within 12 years, he got the Chemistry Nobel Prize for discovering Grignard reagents. So such important reagents are. What are Grignard reagents? Alkyl magnesium halides. Alkyl magnesium halides. Alkyl magnesium halides are generally called as Grignard reagents. Alkyl magnesium halides are generally called as Grignard reagents. When we look at the ionic nature of Grignard reagents, generally magnesium second group cation, it will have +2 charge. Halogens, they'll have -1 charge. So altogether, because these are neutral, alkyl group will have -1 charge. So in a Grignard reagent, alkyl group is having -1 charge, magnesium +2, halogen -1. Or we can simply say RMgx as minus and plus. Now we will look at the nomenclature of some of the Grignard reagents. The simplest among Grignard reagents is methyl magnesium bromide. We can call it as methyl magnesium bromide, or in short, we can also call it as methyl Grignard. Methyl Grignard. So if we have an ethyl group, it is called ethyl Grignard. If we have some cyclohexyl group, it is called cyclohexyl Grignard. Cyclohexyl Grignard. Similarly, we can also have a Grignard reagent with alkene. This is called vinyl Grignard. The simple alkene is called vinyl, so it is called vinyl Grignard. We can also have allyl Grignard. allyl Grignard. If the Grignard reagent is on a triple bond, it is called acetylenic Grignard. Acetylenic Grignard. Similar to allyl, we also have propargyl Grignard. This is allyl Grignard. This is propargyl Grignard. Similarly, we also have phenyl Grignard, and benzyl Grignard. I have given examples with bromine only, but it is also possible to have Grignard reagents with chlorine and iodine. For simplicity, I have mentioned bromine in all the reagents. Now we will look at the preparation of Grignard reagents. Generally, Grignard reagents are prepared using magnesium turnings. Generally, these magnesium turnings has to be activated, or we can also use Reiki magnesium in place of magnesium turnings. How do we Reiki magnesium is nothing but it is a powdered magnesium which is having large surface area, so it is highly reactive. If we use magnesium turnings, we need to activate it. Generally, magnesium, an electropositive element, will generally undergo air oxidation to magnesium oxide. So the metal surface of magnesium turnings will be magnesium oxide. But magnesium oxide will not involve in Grignard reagent formation. So for that, we will activate magnesium turnings. What we will do is, we will treat magnesium turnings, we will wash with HCl. So concentrated HCl. When we wash magnesium turnings, oxide layer will be removed so that these will be activated. How do we prepare Grignard reagents? We will prepare Grignard reagents by reacting magnesium turnings with alkyl halide in presence of a small amount of iodine catalyst, dry ether. Generally, the best solvent for Grignard reagents preparation is dry ether. Then we will reflex it under nitrogen atmosphere. So what we will get is Grignard reagent, or MgX. Generally, it will undergo oxidative addition process. The overall reaction is oxidative addition process, but I'll tell you the mechanism also. How these Grignard reagents will be formed from alkyl halides and magnesium. When we have an alkyl halide and an electropositive metal is added to that, generally electropositive metals will give electrons. Magnesium, a divalent cation, so it generates 2 electrons. Among Rx, R positively charged, X negatively charged. So the 2 electrons will be given to R plus, it becomes R minus. Then this R minus will undergo nucleophilic substitution with another alkyl halide. One alkyl halide becomes R minus. This will undergo nucleophilic substitution with another alkyl halide. So it is the dimerization process MgX2. This MgX2 will further react with magnesium to generate two MgX radicals. This MgX radical will further react with alkyl halide to generate R radical and again MgX2. This MgX2 again will involve in a reaction with magnesium and generate MgX radical. The generated R radical and the remaining MgX radical. So out of the two, one is reacted here, another one is there. These two will combine to give Grignard reagent. Now why we are adding iodine? We are adding iodine to magnesium to generate magnesium iodide. Why should we have magnesium iodide? Because MgX2, if I say iodine, MgX2 is the main intermediate which is involved in the generation of Grignard reagents. How we are generating MgX2? We are generating MgX2 by reaction between alkyl halide and magnesium. So this alkyl halide, it is undergoing dimerization. It is a byproduct. It is not useful for us. Right? What is the useful product? Grignard reagent is the useful product. So in order to avoid this reaction, what we will generally do is we first add magnesium, iodine to magnesium, little bit, okay, just catalytic amount, 100 milligrams or half gram or something like that. When we add iodine to magnesium, it generates magnesium iodide. Then the magnesium iodide will further react with magnesium to generate magnesium iodide radical. That magnesium iodide radical will react with alkyl halide so that it generates R radical. That R radical will generate Grignard reagent. So to avoid loss of alkyl halide in the first step, we generally use iodine as a catalyst to activate the magnesium. Once magnesium is activated, that means magnesium halide is formed, that will further convert it to Grignard reagent.